the first lecture of Ricardo Martinez.
Thank you.
So it's 1 hour and 15 minutes of discussions, but you can interrupt any time.
Yeah, please do interrupt.
Yeah.
Well, thank you. First of all, thank you, Pedro, for organizing this school. I think it's the second time I teach, and it's one of the best experiences. So I have two questions before I start. The first one is, how many of you like biology? Half of you are lying. How many of you is the first time that are having lectures outside your country, if you are not from Brazil? Okay, first time lectures in English? Okay, I speak Spanish and Portuguese, so don't make language a barrier to ask me questions outside or wherever, okay? Try to ask in English, it's a good practice, but if it's really hard for you, we try first in English and then we can, okay? But don't make language a problem for asking questions. So what I'm going to do in my course, I have 4 lectures. The title of the course is a little bit misleading in the sense that I'm not going to cover random walks in the 4 lectures. What I'm going to do is I'm going to try to give you an overview of approaches, techniques that you can use to describe stochastic dynamics, probabilistic processes. And we are going to apply them to one very simple problem that we'll see we can motivate in physics, in biology, in many disciplines, and then we're going to apply this formalism to a biological problem that is a little bit trickier, so you see the limitations and so on and so forth. Okay, when we study these stochastic processes, there is an important component of the techniques that we use that are numerical simulations. I'm not going to show any of that because most of the things I'm going to do are in the Blackboard, so I'm going to teach you analytical techniques and ways in describing that. And the final disclaimer I start writing in the Blackboard is that, especially today, I am going to sacrifice a lot of mathematical rigor in terms, in the benefit of giving you, helping you construct intuition. So this means that at some point I'm going to take continuous limits in a way that you will say, well, this is not the way it should be done. The bibliography I gave you, there are 2 books in which they really do this formally, and one of them is written for physicists, the other one is written for mathematicians, and they will make these limits with rigor. And if you really want to go into the mathematical formalism of stochastic processes, I recommend you to look at these books once you switch on your brain in my lectures, okay? So I think there is no course in introducing stochastic processes that does not start with a problem of tossing a coin. So imagine that you have a coin. Our coin is not tricked by anyone, so it's a fair coin. And we are going to do a series of experiments in which we are going to throw the coin. That is what tossing a coin means. And sometimes we will get a head, and sometimes we will get the other side of the head, that I always forget the name, is a tail. Okay? So in this experiment, if the coin is fair, I have a probability 1/2 of getting heads, and I have a probability 1/2 of getting tails. Okay? The next thing that I can do is I can define a one-dimensional space. Let's say my discrete space has a space in A, and this should be all the same, of course, all the time. Let me put here the space A, and this is going to be the time. So every time I flip my coin, I will lead my time past some interval, let's call it tau. And whenever I get a tail, my virtual particle that I have here, my particle, when I get a tail, is going to go, let's say, to the right. So I keep consistency here. So let's say this is positive A and this is negative A. So imagine that you run your experiment. This is tossing my coin. and you do your first experiment, and let's say you get T. In the mapping that I'm doing, T means right, and H means left. So if I get a T here, my particle is going to go to the right. Let's assume that the right, well, this is not very convenient, so maybe let's do, yeah, well, it's fine. This is positive A, so this would be the rate, and this is minus A, minus 2A, plus 2A, and so on and so forth. So I get a T, I get a right, I am at 0, and then eventually I jump to this place. Then I get another result from my coin. Let's say I get another T. So I stay here, and then I jump again to the right. And then, I don't know, I get an H, so I should go to the left. And you can keep repeating your sequence of experiments many, many times, and you will construct this kind of step trajectories. Okay, so far, everything is very simple. Something that I am assuming here, and I didn't tell you, and is extremely important, is that my experiments, every time I toss the coin, they are completely independent from each other. So this means that the result of me flipping my coin does not depend on what I did before. That's why I chose flipping a coin as an example, instead of asking you left or right, because if I ask you to give me left or right, I am pretty sure we will get anything but random, because it's really hard to create random sequences. And that's something that, for example, if you are interested in these kind of questions, if you want to implement this in the computer, is one of the important algorithms behind all these processes, is how to generate randomness. It's as easy as it looks like. It's not that easy. Great. The second assumption that I'm making, of course, is that my coin is always the same. Because if not, here I'm not being extremely fair with my experiment. Okay, so I'm doing a series of experiments that are all identical, and they are independent from each other. If we want to formalize these assumptions, what this means is that the stochastic process that I am generating via this mapping of tossing a coin towards displacements in a one-dimensional discrete space meets what it's called the Markovian property, which means that the next step in my stochastic process only depends on the present. It does not depend on the past. And this is what I'm going to assume in the whole week. Okay, I'm not going to assume during my week that my systems have any memory, and that the next step, I don't know, if you think about this of an animal moving, then you can tell me, but the animal has memory. So in my lectures, everything is going to be memoryless. Okay, and that's going, of course, to simplify the math tremendously. Okay? Great. So under these very simple assumptions, a way of characterizing this stochastic dynamics, instead of generating this coin tossing experiments many, many times, would be in terms of what? I ask a lot of questions what I teach, so you wake up a little bit. How would you describe the dynamics of my particle that is jumping from left to right? Sorry? Random walk is the name. What I'm doing here is a symmetric random walk. For those of you that either took courses on this or read the notes that I suggested, this is a symmetric random walk, what I'm doing here. But if I want to describe this mathematically, and then I want to measure things, I want to calculate things, how would you describe this process? Sorry? Oh, well, we are flying back there. You can go have lunch if you want today and come back tomorrow. But the master equation describes what? The distribution. One way of describing this is, well, I can make slices at my time t here, and for every time t, I can try to describe the probability that my particle is, let's say, at node x here at time t. And I can try to write a dynamical equation for this probability distribution function. Another way would be to give a differential equation for the position of the particle, right? This is going to be a little bit trickier than what you are used to, because the dynamics is stochastic, and therefore you cannot write something like, for example, I don't know, Newton's law for gravitation of planets, for example, right? So what we are going to do today, and that's why I'm going to sacrifice a lot of rigor, is we are going to learn ways in which I can describe my systems in terms of the probability distribution function, in terms of differential equations for the trajectory, and we are going to see how can we jump from one to the other. And we are going to try to construct a map that allows us to understand how all these different ways of describing systems are connected to each other. Okay? That's what we are going to do today. It's a lot of material, so let's try to speed up a little bit here. So, in the simple case that I am treating now, where I have discrete time and I have discrete space, I can say, well, what is the probability that my particle is at position x at time n plus 1 tau? The probability, the particle can get to this node x from their two neighbors. So one possibility is that at time n times tau, the particle was at, sorry. The particle was on the left, and then jump to the right. Remember that the probabilities are 1/2 always. And the other option is that it was on the right, and it jumped to the left, right? This is very simple, in principle. So once we have this, and of course we need to also provide an initial condition. Let's say the probability that the particle at time 0 is in the origin is 1. So I start with my particle in the origin, and then I have this recurrence that will tell me how the particle is going to be located over time. What is the first thing that you do if you have this recurrence relationship here? What is the first thing that you would try to do? General expression for what? Okay, that's a great answer. It's the first time I ask this and someone tells me to solve this, right? Usually people tell me, I will throw it in the computer, I will do a Taylor expansion, I will do this. Well, the first thing you should do is try to solve it, especially because in this case, this is extremely, I mean, it's possible to solve this. So how can we solve this? At the end, when we have these trajectories, what we have is a sequence of jumps to the left and to the right, right? So imagine that I have generated a trajectory, and I have, well, let's use the 3 that I had there, which was right, right, left, right, right, left, left, right, 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 whatever. This looks like the outcome of some elections. And in here I have n elements, right? Because I've done n jumps, and I'm interested in computing what is the probability that my particle is at a given node after n jumps. So if I have n elements here, I will be able to just commute in all these directions, left, right. I will be able to generate a lot of sequences of a lot of trajectories. What is the probability? Remember that I want to calculate the probability that I am at x after n jumps. So the first thing that I need to isolate, let's say, is from all the possible trajectories that I can generate, how many of those will take me to x, right? There are many ways in which I can go from 0 to x. Let's say here I have 4 jumps. So for example, one possibility is the one that I draw, but another possible trajectory would be that I do this, this, right? This is another option, and you can play around with it. This is a very good exercise if you are not familiar with probability, for you to get an idea of how you count all these paths, and do it with a small n, because otherwise, well, things get nasty. So what is the probability that, given I have n steps, I generate one specific trajectory here? Well, the probability that I get left or right in each of these experiments is 1/2, right? And how many elements do I have? I have n. So the probability that I generate a specific trajectory is 1/2 to the power of n, the number of elements that I have. But now I need to take into account that I can go from 0 to n in many different ways, right? So the probability that I get x after n steps is the probability of one of the trajectories times the number of trajectories that will take me to x. No? Okay. How do I compute the number of trajectories that will take me to x? Okay. Yeah, to jump up or down, to go to, yes? Perfect. Okay, perfect. So if I want to go here, I need to make n jumps to the right, right? And I know that n to the right plus n to the l is n. And I also know that x is n minus r, n sub r minus n sub l, right? So with these two relationships, you can obtain, I mean, you can eliminate, you can write everything, you can write nr and nl in terms of x and n, and basically what you would get from nr is that it's equal to x here. And for nl, so basically the probability that I am at the position x after n steps is going to be 1/2 to the power of n, and here, as we said, I need to take into account all the combinations of n steps with nr steps to the right, which is equal to 1/2, and then here I can just write n 1 plus x to a here. So a few observations about this result, which is our first result. The first one is that here we're already getting some first conclusion, which is that because nr here has to be an integer number, right? Not all the nodes are accessible with all the number of jumps. Of course, if I have 2 jumps, or if I have 3 jumps, I will not be able to go to odd nodes in my lattice, in my one-dimensional system. Okay. The second observation that I get is that, of course, as we were expecting, and this is something we're going to compute now, as I have more jumps in my system, the number of nodes that become visitable for me is going to increase, yes. Why do I use NR? I could use NL as well. Yeah. You can actually, I have, that I forgot to tell you, I have a problem list that will cover both problems that go a little bit beyond what we did, and also cover some of the calculations that I've done in the Blackboard that maybe when you see them sound intuitive, but it's a good exercise for you to sit down and actually do them. There are not so many. I think there are like 8, which means that if I give you 8, it's important that you try to do, maybe not the 8, but 6. I prefer to give few exercises so you do all of them, rather than giving you 30 exercises and then you don't know from where to start, okay? Yes? Actually, yes, that is the second observation that I was going to say that I forgot. If you check notes, many textbooks on this, many of them will assume tau and a equal to 1. That's why I forgot to put it there. I am not doing that because, as I've told you, I'm going to try to take some limits, and then I want to keep a and tau, so then we see how we take them to be small and these kind of things. Okay? But usually, if you check these calculations, you will see that they disappear. Yes? Sorry? Yes? Because I forgot to put it. That's good. So here we have the distribution, the probability distribution function for the position of the particle after n steps. One of the problems that you have in the list that I'm going to share with you is to show that when n gets very large here, this distribution here converges to what? Do you know that? To a Gaussian distribution with mean and variance? Well, mean 0, I tell you, I cheat. The easy one is for me. Sigma square, 1/4. NA square. One of the problem is explained in a way that is you almost have to copy the problem and then do tiny calculations in between the steps that I give you for these problems. If we have time at the end of the lecture, we can sketch the calculation, but I know myself and I know I speak a lot, so I prefer to leave that as a problem and move forward. What I do prepare to convince you, and this is the only slide I'm going to use today, I think school should be in the Blackboard, is comparison. We can compare them, right? So what you see there, for example, is the blue line is the normal distribution that we would get when n gets very large, and the red dots is the discrete exact probability distribution function. That is for very few jumps, 4 jumps. You see that it's already, it's not that bad, but it's not good. And of course, as I increase the number of steps, you see that they converge, right? So again, in the problem, in the exercise list, you have this problem. You only need to use the central limit theorem and rewrite the random walk in terms of a sum of random variables, and you get there. If you've solved this problem, then you don't need to do it. If you haven't, please do it. And if you have questions, I'm here the whole afternoon, so you can come and we can work through it. Once you have your attempts, of course. Great. So we have already, let's build our scheme here. So we have already what we've called the discrete random walk. We've solved the recurrence relationship to obtain Px of t discrete. Let's call it discrete. And then we've taken n going to infinity, and what we get is a normal distribution of mean 0 and variance NA square. So this is the first path that we have, just from solving one recurrence relationship. Yes, questions? How can the variance depend on the number of jumps? If the number of jumps set to go to infinity. So we have a random walk that is going left and right with the same probability. The fact that the variance goes to infinity or grows as the number of jump grows, what is telling us? Look at the, actually it's nice that we have the distributions. Basically, as I have more steps, my particle is going to be more delocalized from the center, if you want. It's going to have higher probability of being covering the infinite. Here, this is an infinite space. I don't have a bounded domain or something like that. Okay. Okay. So let's move. Great. So let's now try to develop the mathematical tools to describe how this probability distribution function changes over time when we, instead of having this discrete time and space, we allow time and space to be continuous variables. So basically, what I'm going to try to do is I'm going to see, or I'm going to develop the tools to write a dynamical equation, a differential equation for this probability distribution function. So to do that, instead of assuming that I can go to the right or to the left with probability 1/2, I'm going to be a little bit more flexible. I'm going to define a probability of jumping to the right that is R. To the left is L. And then I have a probability of not moving at all that I'm going to call N. And of course, the sum of these three quantities has to be equal to 1. If I, on top of that, constrain myself to symmetric random walks, which means that the probability of going to jumping to the right and to the left is the same, basically what I'm going to assume is that R is equal to L, and I'm going to call this M. And therefore, N is going to be 1 minus 2M. So under these conditions, I can rewrite, still in discrete time and space, my recurrence relationship. And now I have this new term that basically accounts for situations in which I am already, or the particle is already at location X and doesn't jump at all. Okay? By the way, I will share with you my handwritten notes. If you are able to get something from them, that's why I'm sticking to the notation I have here, okay? Great. So if I want to get from here a dynamical equation, the first thing that I'm going to do is I'm going to reorder things here a little bit. And this is M px minus A and tau plus px plus A and tau minus 2M p x n tau. Let me now define a time. T is going to be equal to n times tau. So basically here what I will have is everywhere I will have p of x at time t, except in the first term on the left where I have t plus tau, and then minus, well, actually, well, let's rewrite everything. T, this is equal to m px minus a t plus px plus a t minus 2px t. There is no, oh yeah, the m is outside. Yes, thank you. Okay, so next thing I can do, if I divide both terms by tau, and tau is small, tau is much, much smaller than the observation time at which I'm looking at my system, or I take the limit of tau going to 0, what I have here is the derivative of the probability distribution function with respect to t. And what I have here is something that we are going to discuss times all these probabilities here. So what I have here is the limit when tau goes to 0 of n divided by tau, which basically is a probability transition rate. So when I go from, and usually if you have studied master equations, or if you take the bibliography books that I gave you to study these things in more detail, the way you introduce these master equations is already in discrete time, in continuous time, sorry, and instead of having probabilities that go to 0 to 1, you have transition rates, you have probability rates that go from 0 to infinity, because they give you the probability per unit time that you observe one of these jumps. And if you want to get a probability, you need to usually integrate these transition rates over time, but if time is small enough, you just multiply your probability rate by the small time at which you are observing your system. That's the way we are going to introduce master equations tomorrow. So the 3 next lectures are going to be all about master equations. So we are going to, for this specific approach, we are going to be a little bit more rigorous. But for today, what I want you to take home from this sketch calculation here is that when I have these recurrence relationships and I describe the underlying dynamics in continuous time but discrete space, what I get is a master equation that is a differential equation for the probability distribution function. Okay? So basically, in my diagram here, if I go to continuous time but discrete space, what I get is the master equation. Of course, you can also, yes. Sorry, this is, I usually don't, my handwriting is not the best one. And of course, here all I'm going to do in the course is master equations in which my random variable is discrete. That's why I'm going to work a lot with master equations. But you can also have master equations describing continuous random variables, and in that case, most of the things that we are going to describe in terms of sums will become integrals, basically. Okay? But we are going to work with discretes that, in my opinion, are the simplest ones. So the next step that I can do, if I want to go to discrete space and discrete time, and let me actually not take the limit in time yet. I can assume that A is very small. I'm going to make an A very, 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 very small. And therefore, I can do a Taylor expansion of all these probabilities around X. And if A is small enough, I'm going to truncate it at second order. Okay? So if you do that, you get to this relationship here. And here is where you will see most of the times this continuous limit taken. Once you assume small time intervals and small space intervals, and then once you get to this expression, you properly take the limit in which A goes to 0 and T goes to 0, both of them, but you need to take them in a particular way. In which both of them are taken in a way in which the ratio between them converges to a constant that is what we call the diffusion coefficient. Okay? So basically what is happening here, what I'm doing when I take this limit, and this, if you get deeper into the topic, you will see that it leads to a lot of mathematical problems when you work with random walks in discrete time and space. What I'm going to assume is that my jumps become infinitesimally small, but infinitely frequent. So they are very, very often, but very, very small, such that the mean square displacement of this particle grows, we will see later, linear in time. Okay? So this constant here is the diffusion constant, if you want. How many of you have taken courses on PDEs? Okay, so some of you know how to solve this equation, I guess. Either you can transform it to Fourier, for example, or okay. So if I take continuous time and continuous space in this diagram here, now it's continuous time and x, the equation at which I arrive is the Fokker-Planck equation. So the Fokker-Planck equation for this very simple random walk that we are analyzing is a diffusion equation. That's why you will see in the notes that I share with you that they call to this approximation a diffusive, I always say that word wrong in English, but I guess it's fine. A diffusive approximation to a discrete random walk. And in general, we will see tomorrow that this random walk can be mapped to describe a variety of problems. For example, imagine that X is, I don't know, the price of houses in Sao Paulo. And then we develop stochastic models of how these prices of the houses go over time. If they were discrete, you can perform a diffusive approximation to that discrete system, and you can always get a partial differential equation that, in general, it's it's easier to handle than master equations in many cases. Remember that for it to work, you need, of course, to have the assumptions that you are taking to be met. Otherwise, this is a problem. The primer. First order. We are going to organize a game tomorrow, which is catch the typos in the blackboard. And the one that catches more gets free cake. Okay. So those of you that have seen this equation before, what is the solution to this equation? It's a Gaussian that spreads on time. Yes, with variance. That. I don't blame you. I always have these problems. It's 2dt, 4dt. What is the dimension? This is one dimension. So the solution to this, and this is another exercise for you to solve, is a normal distribution with mean 0 and sigma squared 2dt. So it's kind of nice that we are getting from the two paths that we started, at least we are in Gaussian, in normal distributions, which adds some hope. All I'm doing here is taking limits on my original problem. So in principle, I should be able to connect these two descriptions somehow, right? How would you try to connect those two descriptions? A little bit. I have n here. This is for you to open up today, because otherwise I won't have time to finish the last step. I can define an observation time, let's say capital T, that is small t, because it's the same thing I defined before, right? And with this, basically sigma square is equal to tau, small t, a square divided by n. Sorry, I'm replacing n. So n is t divided by tau. And here I stop because I want you to sit down and at least copy the equations and realize the relationships. But it's already there. You just need to define a diffusion in a way that matches what you have there. But do it. Okay? So let me just finish the last 15 minutes. So we've discussed different ways in which we can describe this stochastic dynamics in terms of the probability distribution function for x, which for us today is the location of the particle, but tomorrow will be number of rabbits or whatever. But we said in the beginning of the lecture that there was another approach to describe these systems that was based on providing equations for generating trajectories of these stochastic dynamics. I'm going to touch on it a little bit only on the fourth lecture, but I think it's also important for you to understand how they fit into this roadmap that we are trying to construct today, or at least trying to sketch. Because constructing this, when I used to teach here, was more or less half of a semester course in the master's. So what I'm doing here is a little bit of sketching, basically. So if I have ways of describing PXT, what I want to get a sense is on how I can develop ways of describing just the trajectory. And this is really important because it has some subtle detail that I want you to reflect on, because it's kind of, I mean, it's not tricky, but you need to think carefully about it. So we are describing stochastic processes in which I don't know with certainty where my particle will be at every time. That's why I give probability distribution functions, right? So all the equations that we've written for this object here, for this distribution, are deterministic equations. So I've written recurrence relationships, I've written partial differential equations. If I give you an initial condition, of course, for the probability distribution function, you know how the probability distribution function will be at a later time. The uncertainty of my stochastic process is encoded here, in the fact that at every time I need to describe my system by a probability distribution function. So I cannot tell you tomorrow in my class there will be 30 students. Well, in your case, yes, because everyone is going to come tomorrow with probability 1. But I should say I have, I don't know, a probability 0.9 that I will have, I don't know, 40 and so on and so forth. On the other hand, when I describe x, if I want to generate trajectories, x is my random variable, and the equation that is going to describe it is going to be an stochastic differential equation. So in the notes that I share with you, they discuss how can you get the stochastic differential equation for a random walk starting from the Fokker-Planck equation. It's not an easy calculation. I don't advise you to go through it this week, because if you study it this week, you won't have time to study other things that might be more relevant for the end of the course, let's say, for the weekend test. But if you are really interested into this, I recommend you to take a look at it, because it's a very elegant derivation. So the way I'm going to introduce this stochastic differential equation for the random walk is also in the notes that I share with you in the book by Raúl Toral and Pere Collet. I think the title is Numerical Methods on Stochastic Processes. And what I'm going to do is I'm going to start with a trajectory, let's say, of my random walk, where I start, here it's my 0, and I have all my a's, and this is the tau. Sorry. This is tau, 2 tau, 3 tau, and so on and so forth. So let's imagine that I have this trajectory, for example, this, and now I go up. Now I go up. And I continue, so on and so forth. And this is what I'm going to call xt. I'm going to define a new process that is going to be x at t plus epsilon minus x time t divided by epsilon. So this is a new process that I define. We can see how it looks like here, right? So in principle, it would be nice to have it down. Well, anyway, t, tau, 2 tau, 3 tau, 4 tau. And here, let me not put anything. I'm going to ask you. So how does this process looks like? So I start here. And as long as xt plus epsilon is equal to xt, my new process is equal to what? To 0. 0, 0, 0, 0, 0, 0, 0. Now what happens when I reach a point in which xt plus epsilon is different to xt? So if I go down, I here will get a peak equal to minus a divided by epsilon. So let me already spoil you a little bit here. How long, what is the width of this peak? Epsilon, great. Then I go back to 0. So this is my down jump, and then we were very lucky in our random experiment that the next one is up. So we can see it already. And then I have another one up, and so on and so forth. So this new process that I've constructed here is a sequence of these shots, let's say. Okay? The fourth exercise that you have, that I don't expect that you solve it, all of them this afternoon, because I know you will have other exercises, but tonight, the night is long, and Sao Paulo is boring. This process is the linear combination of two Gaussian processes, and we know that when the number of steps is long enough. We know that because we computed these distributions already, right? So this is the only step in which I don't have exercises for you to prove, and you are going to believe me. But it's related to some of the tools that you will use to solve the exercises. If I have a linear combination of two Gaussian processes, then the resulting Gaussian process is also a Gaussian process. And therefore, I can fully describe it with two things. The first one is the mean. And the second one is the 2 times correlation function, which is a very important object describing stochastic processes. The mean, in this case, is going to be 0. Why? Because I have probability 1/2 of these shots being positive or negative, and they have the same value when they are up and down. So it's kind of easy to see it. It's even easier if you take the mean value here, mean value here, and mean value here. The mean value is a linear operation, so you get 0, because the mean value of x is 0. The correlation function is the exercise that you have to compute. But how would you expect this correlation function to look like? Oh, it's 0? Who, raise your hand if you think that it's 0. You need to stick to your bill. Oh, come on. So how would you compute the correlation function? Let's do it simple. Let's do it for 1 pulse. This mean value, basically what I need to do is I need to compute the product of my stochastic process with itself and sliding it over itself, right? So let's do t minus t prime here. When t minus t prime is equal to 0, what is this mean value here? This is simple. It's the product of it's A? Okay, then let's put here a question mark. But it's not 0, right? We all agree with it, with that. I'm going to put a question mark because it's not A, but I want you to calculate that. And basically, as I slide this pulse over itself, the correlation function is going to be related by the overlap between the two pulses as they move with delay. This is, again, this is intuition that I want to build on you. You need to solve this. You need to calculate this. And you will see that the intuition is correct. So basically, only thing I'm going to tell you is that it's a triangular function because it's the only thing I need. And it has a maximum value here, and it has some extent. Actually, I think you are lucky because I need to give the numbers to take the limits. Final question before you have 15 minutes to ask questions. And of course, your questions at the end of the lecture cannot be the questions that I left you to work on the afternoon, because that is cheating. What happens if now I take the limit that I was taking before? What happens to this function here? Delta? Yeah, who said delta? Don't be afraid. Yeah. Which is the amplitude? So the only thing I'm going to ask you to do this afternoon, I mean, I'm going to give you problems. I recommend you to do them. But I also want you to use your time in a smart way, in the sense that you get to the exams that you have in the weekend that are important in the best way. So don't use your time that much into getting this correlation function, because it's not that important for the next lectures. You can try to solve that once you are at home, or if you have some free time at night. If you solve it at home and you have troubles, you can write me an email and we can, that's fine. I'm not going to disappear after I'm gone from the school. But please take your time to think carefully about how the diffusion coefficient that we define is going to appear here. It's already written there. So you will get here some diffusion coefficient. And think then that once I take the limit of epsilon going to 0 in this process, what is this equal to? The derivative. For us today, it's a derivative. If there is a mathematician here, it's going to kill, well, I would probably be done many, many minutes ago. So what I'm saying is that this new process that I define, when I take this epsilon to be very small, is the derivative of the position of the random walk. It's a Gaussian process because it's the linear combination of two Gaussian processes. And it's defined by a mean that is equal to 0 and a 2 times correlation function that is this delta the Dirac distribution. So in principle, if you are able to plug here a diffusion, this equation is going to give you trajectories that are sampled from this probability distribution function that we were defining before. And it will be a complementary way of describing this system. For example, if with your computer you simulate a lot of these equations, I don't know, 1,000,000 for 10 times, from time 0 to time 100, and you pick the position of the value of this x at time 90, and you construct a normalized histogram, you will get the distribution that you obtained before. Okay? That's another nice exercise if you want to play with the computer. Okay? Questions? Oh, thank you. So these are the books that you should use to study these things properly before I forget. Gardner is more mathematical, Van Kampen is more for physicists, but both of them are definitely more rigorous than what I did here today. Questions? If there are no questions, then we can do the first exercise. Okay, yeah, questions. Why they call? Why the pulses have width? Here? Okay, so this is xt. No? Xt. Let's plot, or let's draw xt plus epsilon. How would xt plus epsilon look like? Displaced. So, for example, when xt is equal to, it's here, how would xt plus epsilon look like? You got it? Great. I love those answers where I have to do nothing. Yes? Yes. 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 So the question was one of the, let's say, tricks that I took out from nowhere is that when I wanted to go from discrete space and time to continuous space and time, I allowed my random walk to also stay in the node, whereas before I was defining my random walk to be with probability 1/2 to the right or to the left. So the idea behind this probability of staying is that when you want to take the time continuous, and I want to take small time intervals, imagine that the probability of, what I'm doing is the probability of going from left to the right in a time tau is 1/2 or 1/2. But when this tau goes to 0, it's smaller, smaller, and smaller, it doesn't need to be 1/2. The symmetry stays because there is still no any external element that will bias my random walk to go one direction or the other. But if this is intuition. If the probability of going to right or left is 1/2 in, let's say, 1 hour, as I shrink my time step, I still have both probabilities to be equal, but they will be smaller, right? Because the probability at which I jump to right or left is 1/2 per hour. So if now I make my hours milliseconds, I need to change from 1/2 per hour to wherever per millisecond. It's still going to be the same left to right because it's the same. And this is the intuition behind going from probabilities to going to transition rates. Yes? Sorry, again, the probability per unit time is not 0. Yes. So here the idea, no, so you're thinking in the right direction. So here the idea is when I describe my system in terms of discrete time and space, I define my time step. First of all, it's deterministic, right? So I know that every tau it jumps. So my time scale is the time scale at which my random walk jumps. That's why usually instead of tau you take 1, right? So I know that I wait a time until my random walk jumps, and I know it jumps with certainty at that time. If now I want to change that time scale at which I'm observing my system, at which I'm observing my random walk, and instead of observing for tau, I observe it for a time tau divided by 10,000, I don't have certainty that my random walk will jump, right? Because I know it jumps at time 1. So if I observe it for a shorter time, and I relax the assumption that the random walk is going to jump with certainty 1 at a time tau, then I have a probability per unit time of observing the event or not. Sí. So he's asking why that forces me to define a probability of staying in that place, because when I take time small, I know the random walk has the chance to stay, right? So I need that term to write the equation. He's asking me if I can solve it if I don't define the probability of staying. So usually, you cannot do this expansion that I did if I don't have the term on staying, because then yeah. No worries. De nada. Yes. You can, if you want, and I repeat what.
I didn't understand the concept of omega t and omega t prime. I don't know if you can explain it.
Omega t and omega t prime.
That's
the correlation function?
Yeah, I mean we have to fix a certain t prime and then move the t, or I didn't understand.
Yeah. So this is basically what you're going to do is you're going to compute the mean value of the stochastic process with itself at different time steps, at different time moments, sorry. So in principle, t and t prime are two arbitrary times, and what you're going to calculate is the mean value of the product of the stochastic process at time t with stochastic with the process at time t prime. And that is going to give you a function of time t and time t prime that is going to tell you how the value at a given time is correlated with the value at another time.
Okay, so t and t prime are not related in first place?
Are not really, sorry?
Related.
No. You will get from this computation, you will get a function that is a function of t and t prime in general.
Okay.
In some cases, you will see that your computation will depend only on t minus t prime, as it was the case here. But I'm not going to enter into that. But in most of the cases that you will be interested unless you, I don't know, start working on.
Can you give a hint about how to solve it?
if I can give you a hint on how to solve it.
Yeah, I mean.
So in the problem list, I give you steps on how to solve it. I tell you, define this, compute this integral, do this, do that.
Where can we find those?
It's going to be in the school webpage probably now, once we go for lunch. Lunch? Question? Lunch. Okay.
Thank you.
Welcome.